Hello everyone, welcome back to my YouTube channel. My name is Srushti. I am in my third semester studying in Sri Venkateshwara College of Engineering in the Department of Computer Science and Engineering. Today I bring forth a very interesting topic in the subject of mathematics, which includes the topic joint probability distribution. Today we are going to learn about what joint probability distribution is and all its different properties, applications, formulas, etc. Now see through the overview of today's video. First is the definition of joint probability distribution, the mathematical formula, essential components, examples, mathematical examples, properties, applications, and conclusion. Let's move on. Definition. A joint probability distribution describes the probability of a multiple random variable taking specific values simultaneously. In similar terms, it provides the likelihood of different combination of outcomes for two or more random variables occurring together. Now let's learn the mathematical formula. The mathematical formula of joint probability distribution depends on two conditions, that is whether the random variables are discrete or continuous. Now let's see if the two random variables are discrete. For two discrete random variables, capital X and capital Y, the joint probability function, mass function, that is the PMF, is denoted as P of capital X is equals to small x, comma capital Y is equals to small y, representing that the probability that capital X takes the values of small x and capital Y takes the values of y simultaneously. The sum of all joint probability over all possible values of x and y must be equal to 1. That is, summation of all x and summation of all y into p of x is equals to x, comma y is equals to y should be equal to 1. For two continuous random variables x and y, the joint probability density function, that is the PDF, is denoted as f of x, comma y. The integral of the joint probability density function, that is the PDF, over the entire range of capital X and y must be equal to 1. That is, integration of entire range 1 and integration entire range f of x, comma y dx into dy should be equal to 1. Now let's learn some essential components. Random variables, variables representing different aspects of the scenario. Sample space, set of all possible outcomes of the random variables. Third one is probability function, assigns probabilities to each combination of values. Fourth one is joint probability mass function or probability density function, mathematical expression for joint probabilities. The fifth one is marginal probability, probability of a single variable without considering others. Now let's learn examples. Two fair dice. Let x be the outcome of the first die and y be the outcome of the second die. The joint probability distribution would be a table showing the probability of each pair x, y. For a fair dice, each combination has a probability of 1 is to 36. That is, the probability that 1 and 1 will come in both the dice is 1 is to 36, and so on. Let's see the second example. Coin toss. Let x be the outcome of the first toss, head or tail, and y be the outcome of the second toss. The joint probability distribution would be P of x is equals to h and y is equals to h is equals to P of head, comma head is equals to 1 by 4 P of x is equals to h and y is equals to t, which is equal to P of head, comma tail is equals to 1 of 4 P of x is equals to t, y is equals to h, which is P of tail, comma head, which is again equal to 1 by 4 P of x is equals to t, y is equals to t, which is equal to P of tail, comma tail is equals to 1. Here it shows that the probability of outcome of h and h, that is head and head, is 1 by 4. Here P of x is equals to h, comma y of h is equals to h represents the probability of getting heads on both the first and the second toss. The next one is P of x is equals to h and y is equals to t, represents the probability of getting heads on the first toss and tails on the second toss. P of x is equals to t and y is equals to h represents the probability of getting tails on the first toss and heads on the second toss. And P of x is equals to t and y is equals to t represents the probability of getting tails on both the first and the second toss. Here you can see that the outcomes is 1 by 4, 1 by 4, 1 by 4, 1 by 4 for all of them. Now let's move on to a mathematical example. Let's consider two events A and B. The joint probability of P of A and B is the probability that both events A and B occur. Suppose P of A is equals to 0.6 and P of B is equals to 0.3. If A and B are independent events, then P of A and B is equals to P into PB. P A and B is equals to 0.6 into 0.3, which will give you 0.8. This is the joint probability of events A and B occurring. If A and B are dependent, the calculation would involve the conditional probability of B given A or vice versa. Now let's move on to the properties. The properties include non-negativity, normalization, marginal probability, conditional probability, and independence. First one, non-negativity. P of capital X is equals to small x, comma capital Y is equals to small y should always be greater than 0 for all x and y. That is, then it should not be negative value -1, -2, etc. It should always be greater than or equal to 0. Next is normalization. Summation and summation of P of capital X is equals to small x, comma capital Y is equals to small y should always be equal to 1 over all possible values. It shouldn't be greater than 1 or lesser than 1. Marginal probability. Summation of P of capital X is equals to X is equals to 1 for discrete variables, or integration of P of capital X is equals to X into dx is equals to 1 for continuous variables. That is, the marginal probability should always be equal to 1 for the summation of all the values in discrete variables and integration of all the values in continuous variables. The next one is conditional probability. P of A or B is equals to P of A and B divided by P of B. Next is independence. P of x and y is equal to P of x into P of y for independent variables, as we have seen in the previous example. Applications. First one, finance. It is used in various forms, for example, profile management, modeling joint probability for asset returns, and risk assessment, analyzing the joint probability of financial events. The second one, it is used in medicines. It is used for disease diagnosis and treatment planning. In disease diagnosis, it analyzes the symptoms and tests result jointly. In treatment planning, it assesses the joint probability of treatment success. The third one is quality control. Manufacturing and process optimization are two main important in quality control. That is, modeling joint probabilities of defectives in different components in manufacturing and identifying areas of quality improvement in process optimization. Machine learning, classification, modeling joint probability distribution of features, and predictive analytics, enhancing accuracy by considering multiple variables. Conclusion. In conclusion, a joint probability distribution is a powerful concept in probability theory that allows us to model and analyze the likelihood of multiple random variables occurring simultaneously. It provides a comprehensive understanding of the relationships and dependencies between different events, enabling us to make informed predictions and decisions in various fields. Thank you for watching our video. I hope you liked it. Please do subscribe and like.